Okay, so we've been talking about fields a lot, magnetic fields. Let's finally bring into it what's kind of been the elephant in the room this whole time, the force, the magnetic force that's actually been causing these things to happen that we've been seeing happen, right? Like when a magnet deflects, things don't move, they don't accelerate, at least without a force acting on them, right? So there must be some kind of force at play here. Let's actually get into what the magnetic force is about and how we can analyze that. Okay, so it says here if a current, it doesn't mean if as like if it does or doesn't, it might not. No, it does. We know it does. We proved it, right? It's saying more like since a current does, or because, right? It's not a matter of if. A current does produce a magnetic field. We've seen that, okay? We've proven it. So because a current produces a magnetic field, it will behave as a magnet, right? As soon as you have a magnetic field, that thing's now a magnet and is thus attracted or repelled by other magnets, okay? Or it might attract metals, okay? Not all metals though. Ferromagnetic metals, right? Ferromagnetic metals, right? Not any old metal. It won't attract aluminum, for example. Okay, it needs to be ferromagnetic, which we talked about before. So two magnetic fields interacting will create a force, right? So you know this, right? When we put the bar magnets together, okay, what happened to them if they were lined up like this, for example? Okay, if they were close enough together, they would accelerate. And as we know from physics 20 and from all of our physics, right? If something is accelerating, there must be a force acting on it. You can't have something go from being at rest to in motion without a force being involved in some way. Okay, so when we placed those two magnetic fields near each other, they interacted in such a way that an attractive force was produced. So now keep that in mind. Two magnetic fields interacting, right, will create a force. It doesn't seem that weird here, okay, but it's going to get a little bit weirder when we think about the magnetic field induced by a current, or at least at first it might seem weird, okay? So it's time for our first kind of equation here, right? We have that. We haven't had one yet in chapter 12 for magnetism, okay? So the magnitude of the force is given by either F equals QV, we'll talk about that little symbol in a sec, or QVB, sorry, remember B is the magnetic field, or F equals ILB, okay? And these are indeed magnitudes, okay? These are magnitudes of the magnetic field. Okay, so when would you use each one? Well, what is I? Remember, I is current, okay? So I would use, you could keep calling this the force. What is the kind of label for the force? It's Fm for the magnetic force. So Fm equals I, current again, L, again, there's that little symbol, E. Okay, when should you use that guy? Well, in the context of current and this thing here, okay, this little L, we are talking about a charge that's in a wire, okay? So I'll get to what each variable means here in a sec. I, of course, is current, right? So I is current, okay? L is going to be, it literally means the length of the wire, okay? So length of wire with an important distinction that symbol is going to involve, okay? And then, of course, B is our magnetic field, okay? So since we're talking about current and a wire, okay, this is going to be, we would use this thing, okay? Use this thing when our moving charges are confined to a wire, okay? Because of that fact that we're talking about a length of wire and a current, okay? This kind of means we're going to do it when moving charges are confined to a wire. Now, technically, this doesn't only apply in a wire, right? L is just the length that it travels through a magnetic field, and I is just coulombs per second, so it doesn't have to be in a wire, but this is kind of always when it ends up making sense. We also have Fm equals Q. The magnetic force equals QVB. Okay, what is Q? Q is still charge. Okay, V, and again, you see that symbol. Okay, that's going to be important. Speed. Okay, and again, B, nothing different there. That's still our magnetic field. Okay, so when do we use this one? We use this one. Notice how there's nothing about the length of a wire. It's just talking about the speed of some charge. So this is when our charge is free to move. Okay, to move through the magnetic field. Okay, I just really want to quickly prove to you that these are not so different. Okay, they kind of come from the same place. So I'm going to start with this equation here, just off to the side. I have that Fm equals IL B. Okay, what is I? How do we get current? Well, current is charge per unit time. So Q over T times some length that's traveling through the wire times B. Okay, hang on. Do you see this? Some length that's traveling through the wire and the amount of time it took it to go through the wire. Hey, how far it went divided by how long it took. Does that sound like something? A distance divided by a time. So what is this? This is just Q V B. So they really are the same idea. One just makes more sense when we're talking about a current carrying conductor, and one makes more sense when we're talking about a free charge moving through a magnetic field. Okay, so I just wanted to point that out, that these aren't very different ideas. They're the same idea, just applied in more convenient ways depending on the situation. Okay, now I've been holding off on this, and it's crucial. What do these symbols mean? Okay, you might recognize those. They mean, okay, the magnetic force only comes from the component of the speed or the component of the wire length that is perpendicular to the magnetic field. Okay, perpendicular to the magnetic field. So only the perpendicular component actually counts towards creating a force. So only M. So if it's going super, super fast, great, but only the perpendicular part of its motion is actually going to end up mattering. So what do I mean by that? If you have some magnetic field, okay, and you have some velocity that it's coming in with, some charge is coming in with some velocity, that's just its V, okay? It has some component that is perpendicular to the magnetic field itself. So when we go to calculate it's the magnetic force it's going to feel because of the magnetic field, right? We are not going to use V. We are going to use only the perpendicular component. Only the perpendicular component. So with this being the angle of entry or the angle of incidence, see how this is the angle that it enters the B field at, right? V, in this case, V perpendicular equals V sine theta, okay? So great that it's going fast this way, but that doesn't count, okay? This Y component, this parallel component, V parallel, does not count at all. Only this will contribute to the magnetic force. Okay, then it asks us to figure out, hey, what are the base units of magnetic field? We have been talking about the magnetic field, but we haven't had to do any calculations with it yet. So we've kind of dodged the conversation of units. No longer can we do that. Let's go ahead and figure it out. Well, Fm equals, I'm going to do IL perpendicular, so only the perpendicular component of the wire, only the amount of the length of the wire that travels perpendicular to the magnetic field counts here. And so rearranging, magnetic field, divide both sides by IL perpendicular equals Fm over IL perpendicular. Okay, so what are the units of a magnetic force? Just like every other force in the universe, the units are newtons. Okay, divided by, hey, what are the units of current? Amps. And what are the units of a length? Meters. So we have newtons per amp meter. Okay, we can probably simplify this a bit more. So let's see. Newtons we know as a kilogram meter per second squared. Okay, not that we probably can, we actually have to because it asks for the base units. Newtons are not a base unit. Okay, kilogram meter per second squared. Amps actually are a base unit, but I know there's seconds here, so we can probably simplify a bit. If we do, whoops, not coulomb seconds, coulombs per second, okay, times meters. I'm just going to go ahead and put these all in square brackets to remind us that we're just doing unit analysis. Okay, that's kind of how we show unit analysis. All right, so still just trying to simplify this out, get our base unit. So now we have kilogram meters per second squared over coulombs per second times meters. I'm just going to defractionify everything. So what I mean by that is if it's being divided, I'm going to put it down. If it's being divided in a denominator, I'll put it up. So kilograms meters, okay, the second squares belongs in the denominator, right? Per second squared. But then we have coulombs per second, but that's a denominator in a denominator, right? So dividing by coulombs per second is the same as multiplying by seconds per coulomb. So that seconds actually gets put up there, and then meters. Okay, let's just do some cancellations. Seconds over seconds squared, so the squared's gone, but we still have seconds in the bottom. Then meters and meters. Okay, there we go. So what is the unit of magnetic field? It is a kilogram per coulomb second. Now, we got kind of sick of calling it that, and so we named them after a very famous physicist who worked a lot with electricity and magnetism by the name of Nikola Tesla. So the unit of magnetism, the standard international unit of magnetism, is the T for the Tesla. Okay, might be more famous now as a car, but Elon Musk actually named the Tesla after Tesla as well. Okay, I'll challenge you to use the other formula, right? Try using that one to derive the same unit. See if you can get the kilogram per coulomb second for that guy as well. Okay, so an electron is moving at 75% the speed of light when it enters a magnetic field with a magnitude of 0.35 Tesla. Okay, we're going to have our B field, our magnetic field. Okay, this is B, our magnetic field. And an electron is moving at 75% the speed of light when it enters a magnetic field. So it's moving at V equals 0.75 C. And it enters, at first, we're going to figure out what happens if the angle it enters at is 90 degrees. In other words, if it's perfectly perpendicular, okay? Okay, question for you. What makes the most sense to use here? ILB or QVB? Well, this is a free electron, right? So it makes the most sense to just say, hey, what's the velocity of the electron? Not to think about the current flowing through a wire per second. So I'm going to use QVB. Hey, especially since we have a V, probably makes sense to use QVB, right? Okay, so it's moving at 75% the speed of light. What is the vertical component of its velocity? Well, it's all of it. We can think of its entry angle as 90 degrees, right? And as we showed up here, how do you get the perpendicular component? If you know its entry angle, well, you do sine theta. Hey, type really quick, or maybe you know this from your math class. Sine of 90 degrees equals 1, right? So we could even put that in. Fm equals Q V sine theta, where theta is the entry angle, okay, in this case, 90 degrees, V sine theta, because that's V perpendicular, times the magnetic field magnitude. And we have that these are all magnitudes as well. The magnitude of the magnetic force is going to be, what's the charge of an electron? It's E times 10 to the negative 19 coulombs. V sine theta, so you can take 0.75. C is on the back of your periodic table. It's the speed of light in a vacuum. Okay, you'll get to know that number very well, especially next unit. 3 times 10 to the 8 meters per second is that, 300,000 kilometers per second. 0.7 sine 90. Again, being kind of facetious here by even putting that in because it's going to be 1, but it doesn't hurt to show you what I mean, times 0.35 Tesla, which as we know are kilograms per coulomb second. If we want to check really quick, we're going to have kilograms per coulomb, okay? So kilograms per coulomb second, so the coulombs would be gone, right? And then coulomb second, so the seconds would get squared. And then we have kilograms meters per second squared with the coulombs gone. Hey, kilogram meter per second squared, that's a Newton. So FMA magnitude of the magnetic force, I got 1.26 times 10 to the negative 11 newtons. Cool. Great. You're saying, okay, what's the direction? Haha, you're going to have to wait for another hand rule for that. Okay, now it's saying, what if, so we'll call this A, okay? Now in B, what if it enters at 45 degrees? So now its entry angle is not 90. Now in B, its angle of entry is 45. So now in B, this is 45 degrees. Where is its component of its velocity that is perpendicular to the magnetic field? Well, you can probably see it, right? It's not this component. That would be parallel. It's this component. So that is V perpendicular, right? That's V parallel, which counts for nothing. If it enters at 45 degrees, how do we get? So again, we're just starting here. Fm equals Q, the charge, times the perpendicular component of its velocity, times the magnitude of the magnetic field. Now we're actually not just being silly by putting it in, or I guess being sticklers by putting it in. We actually need to say that that equals Q times V sine theta, okay, times the magnetic field strength, which is going to be 1.6 times 10 to the negative 19 coulombs, okay, times V is still 75% the speed of light, so still 0.75 times 3 times 10 to the 8 meters per second. Sine theta, though, now is not just going to be sine 90 and be 1. It's going to be sine of 45 degrees and be 1/2, okay, times the magnetic field strength, which is 0.35 Tesla. All right, multiply that all out. What do you get? The magnetic field strength, if it comes in at 45 degrees, is going to be 8.91 times 10 to the negative, times 10 to the negative 12 newtons. Oops, and I apologize. I think I said sine 45 was 1/2. I'm thinking of sine 30. Sine 45 is 1/√2. Sorry. Just noticed, by the way, too, whoops, I was only supposed to have how many sig digs? 2, right? 2. Okay. Finally, what if its angle of entry now is 0 degrees? So the angle between the magnetic field and it is now going to be 0 degrees. What does that mean that it comes in looking like? Well, how do I make this angle 0 degrees? I keep making this smaller and smaller and smaller, right? So I'm going to show you over here. If it enters at 0 degrees, it enters perfectly parallel, right? Two lines that have an angle between each other of 0 degrees, well, those are parallel lines, okay? So now, what's V perpendicular? What's the perpendicular component of its entry speed? Well, it's 0, right? If you can kind of tell from looking at it. Or we could also tell ourselves what's sine of 0? Well, you might know from math class, sine of 0 is 0. So again, Fm, the magnetic force, is going to be equal to Q times the perpendicular component of its velocity times the magnetic field strength equals, if we want, we could just say now that the perpendicular component is 0. But if we want to be really rigorous, we could say Q equals V sine theta times B, which is 1.6 times 10 to the negative 19 coulombs, times still 75% the speed of light in a vacuum. Okay, this electron's going pretty quick. Times sine theta, so sine of 0, which again is going to be 0, times B, 0.35 Tesla. And if you want to check my work and plug it in your calculator, you can, but I'm telling you, it's going to be 0 newtons. So this thing will feel no force if it does not have a perpendicular component. This seems kind of weird, doesn't it? Well, electromagnetism can be kind of weird at first. So in order to feel a magnetic force, some moving charge, whether it's in a wire or not, needs to have a component of its velocity that is perpendicular to the magnetic field it is moving through. Okay, now I get that it can seem kind of weird at first why this magnetic force is perpendicular to not only the speed of the moving charge, but particularly the external magnetic field. If you are okay to just accept that it is, then you could just skip past this part. But for those of you that will not sleep tonight, unless you can kind of see why, or at least have a bit of a conception why, okay, let's just imagine a scenario, okay? So I'm going to take kind of that same field as before, So this field here, okay, now we're going to look at it from down here. So now our eye is in the paper kind of looking this way at it. So we're just going to actually draw the magnets causing the field just to help us visualize this. So if we have here, so I have here two kind of magnets, a north pole and a south pole that are of course going to have a magnetic field between them. That's going to be our external magnetic field. And what are we going to do? Let's send an electron. So let's send an electron into the page through that external magnetic field. So let's think about the field lines. The external field here, what are they going to look like between these two? Well, they're going to be leaving north, entering south, right? Leaving north, entering south. Now, I just told you this electron is moving. It's going into the page. So it's an electron, negative charge. Take your left hand and figure out what the magnetic field that it induces is going to look like. So if you put your left thumb into the page, you'll notice that your fingers curl this way, right? So there is the magnetic field induced by that thing's moving charge. And so what we're saying here is that, okay, the interaction between the magnetic field induced by the moving electron and the external magnetic field, okay, are going to cause a force that is perpendicular to both of those directions. So if you think about it, okay, we have this going this way, right? We have this going side to side horizontally. So I'm going to use something that's kind of called the replacement magnet method. And all that does is help us visualize what kind of interactions are going on here. So I'm going to take this. This is a magnetic field this way, right? But we can kind of say, okay, if this is magnetic field is going this way, it's like there's a smaller magnet here, right? With a magnetic field traveling through it that has it's entering south, right? Magnetic field lines would enter south and they would leave north, okay? Now down here, same thing. Where would field lines go? They would enter south and leave north. Okay with that so far? Now let's look at what about on our induced magnetic field from our electron? Well, we would have, this one's going this way. Okay, easy enough. So at this top point here, what could we replace that with? What would the magnetic field look like if we had a bar magnet here? Or how could we use a bar magnet to produce the same magnetic field that we see induced at that point? Well, it would, right, if it's traveling kind of to the left of your screen, it would enter south and leave north. Okay, now let's do the same down here. Enter south, and leave north. So what is the resulting is we just use our, if we kind of think about it as replacement magnets, what kind of force would these two magnets feel? And what kind of force would these two magnets feel? The two kind of replacement magnets that are closer to each other, right? So again, this is just the magnet that if I placed there, I would end up with kind of the same field, right? Because that's what we're looking at is the field. Same thing here. If I put this magnet here, I would end up with the field looking the same, and same here, and same here. But again, what would these feel? Well, would they feel attraction or repulsion? You've got a north next to a south and a south next to a north. So these are going to feel attraction. Which way? Up towards the top of your page. Which way would these feel? They would feel repulsion, right? North, north, south, south. They would push this charge up again towards the top of your page. So when you have your electron going into the page, okay, you have your magnetic field going left to right, and what's the resultant magnetic force? Up. So we kind of have three things that are all perpendicular to each other. If we wanted to visualize this on like an X, Y, Z axis, we would have our Y going side to side. That would be our magnetic field, right? We would have our force magnetic going straight up. Okay, that's Fm. And how do we show on it? You might not have seen an XYZ axis before, okay, but how do we show something going away from us on this is actually, it gets called the x-axis, the way I'm going to draw it. That is the V, right? So, okay, so that kind of replacement method should at least help to ease your concerns about why is this force perpendicular? We are going to now really jump into the third hand rule, but I want you to come back to this after we've done the third hand rule, take a look at it again, and see if it agrees or not. So just to provide a quick visual, because I know you might not, of what you just saw, you might not have actually ever seen an XYZ axis before. It's a little weird to look at first. So what is this actually showing? So it's kind of showing the V is going away from you on what's usually called the X axis in these. The magnetic field, this is usually called the Y axis, and then the FM is actually called the Z axis. So the Z axis is straight up and down. There's that. As we know, the electron was moving away from us, okay? So we kind of say it's going away like that, right? Going away like that. And then our magnetic field would be off to the right. So what it ends up looking like is this, right? This is all that's showing. Okay, so they are perpendicular to one another, right? Force and velocity are perpendicular, field and force are perpendicular to each other, and then velocity and field are perpendicular to each other. Three things perpendicular. Okay, so just again, another visualization. They've chosen to label it differently a bit here, and the colors are different, but right, this kind of is better than I could draw it. So you have your, in ours, this would have been the magnetic field off this way, perpendicular, of course, 90 degrees to where our magnetic force was up to the top of the page, and then our velocity would be along what they call the negative Z axis here into the plane of the page. So how can you keep these three mutually perpendicular directions all straight? Well, luckily, there are two things on the ends of your arms that can point in three perpendicular directions at once. Okay, so let's learn. So it's time for a new hand rule. Now, because we are dealing with, again, perpendicularity here, okay, we are going to need a hand rule. The third hand rule, okay? Now, the big difference between the first two hand rules and the third hand rule is that in the first two hand rules, we were always kind of talking about a charge and a magnetic field that matched each other, right? So we were talking about a moving charge and the magnetic field it induced. Might have been circular, might have been straight, but either way, it was one charge and the magnetic field it induced. In the case of our third hand rule, okay, we are talking this B field, this magnetic field does not actually belong to the moving charge. This is an external magnetic field. So one that did not come, it's not induced by the charge. It was already there. Okay, it's external to the charge, like the one we were looking at before. We will, again, I'll print off some big pictures and we can do it over camera so you can actually see me, because me talking about a hand rule is hard to wrap your head around. But first, let me just get the rules down. Okay, we use the third hand rule for a force created by a magnetic field that is perpendicular, okay, must be perpendicular to a moving charge. Okay, so this is kind of the first time you've had to deal with a force that works this way. You've never had a force that acted perpendicular to the field which caused it. Never. The closest we've gotten to even that is in an electric field, you could have a force in the opposite direction, so anti-parallel to the field lines, right? How would you get that? Well, with a negative charge in an electric field, it will move in the direction opposite of the field lines, because electric field is defined as what a positive would do, right? But nothing was ever this weird. Nothing was perpendicular to the field. And again, that has to do with the interactions between the induced magnetic field and the pre-existing external magnetic field. Okay, so your fingers in the third hand rule are in the direction of the magnetic field. Okay, your fingers are in the direction of the magnetic field. And then your thumb, okay, just like in our first hand rule here, your thumb points in the direction of the moving charge. So what do you think? Which hand are you going to use if the moving charge is negative? Okay, you guessed it. If the moving charge is negative, use your left hand. Okay, again, left thumb if the moving charge is negative. Whoops. Okay, so left for negative charges, left hand, but obviously your left thumb too. Okay, right for positive charges. Okay, so this third hand rule actually kind of applies sort of the same for your fingers and your thumb. It's the same as the first hand rule. The difference is, though, this magnetic field is not induced. It's the external one. But like the first hand rule, thumb is the direction of the charge motion, and fingers are the magnetic field. Okay. Your palm, and I like this one, this is what I like about this one, your palm shows the direction of the magnetic force. And when I actually get on camera and show you, you'll see. But it's like a push, right? A force is a push. So your palm is actually going to push in the direction of the magnetic force that results from this charge moving in a field. Okay, there is a bit of a trick that some people use. Honestly, I don't think of it because to me it makes sense. You got your field, your fingers, you got your charge moving along your thumb, and then you push with your force. But some people like to remember FBI for they go from palm, fingers to thumb, palm, fingers, thumb. It goes FBI. I have a problem with it though. It's only I on one hand, right? Which hand is it I? Remember, I is current. Okay, which leads me to my big problem with this picture. Do you see it? Sticks out like a sore thumb. Okay, this thumb should not be current. Why? Because what hand does it belong to? This is a left hand. This is a left hand. Why are they showing current with their left hand? Okay, so make that note for yourself. They should not be using their left hand for this. If they're either that or this should be electron flow, not current. Okay, so if this is left hand rule, okay, if they're using their left hand rule, let's just say current, this is a left hand. So should be electron flow. Okay, this is a bad picture. But the force I agree with. Okay, so if this was electron flow, then this is the direction that a negative charge would feel. So if you had a magnetic field along the axis of your fingers and your electron, or I guess it doesn't have to be an electron, any negative charge was going this way, then your force would be up that way. Okay, so again, hand rules are cool and all, but let's not just jump into them until we've kind of proven them with something physical, right? Or at least built some confidence with it. Seeing is believing, right? So third hand rule, okay? What I have here is actually one of my favorite kind of physics doohickeys I've come across. Okay, Mr. Van Thiel showed me this. I thought it was so cool. So we have, okay, essentially what this thing is a big magnet, okay? A big magnet with a south pole here and a north pole here, a big flat magnet, okay? Let's test it out to make sure I'm not lying to you, but see, when you put it on top, field lines are up. So what does that mean? They're leaving here, right? Must be north, okay? And then when you put it underneath, same thing. They're going up, so they are entering south there, right? We have our, okay, you can kind of see it flip. So North Pole up here, South Pole down here. So what does that mean? What is the direction of the magnetic field lines on top? How would we show that with our hand rule? Okay, well, they're going to be all up, right? Field lines go from south to north and then back around to south. So at this point here, the field looks like this. The magnetic field is going up like this. Let's try and apply, that's the first ingredient to our third hand rule, okay? So in our third hand rule, we also have a moving charge. The difference in the magnetic field that we just talked about compared to the first and second is in the first and second, those magnetic fields were induced by a moving charge. Now we have a magnetic field whether there's a moving charge or not, okay? And that's the one we're interested in. We're going to call it an external magnetic field, okay? What's the other part? We have either current or not either. We have currents and moving charges, right? So what is going on here? You can see, okay, or maybe you can't, but I have hooked up, okay, a wire to kind of just a stud on there, right? And on here. So if I were to hook it up to the battery, the circuit would not quite be complete. You'll notice there's nothing in there conductive. This is actually all wood, right? So this is conductive, this metal, this is conductive. You essentially have two parallel plates, but there's no way for charge to actually go across, okay? A charge would not be flowing. What I can use though is this wire, okay? I can use this wire to complete the circuit. I don't have it hooked up to the battery yet, okay? But let's just think about this. So I have this black one. I will hook that up to the negative terminal, okay? And I'll hook the red one up to the positive terminal, okay? Let's just think for a sec. So electrons are going to be, I'm just going to tilt it a bit. There you go. Electrons are going to be coming. They're going to be on this plate, okay? They're going to then travel to complete the circuit. They're going to want to travel across this wire, right, to get over here to eventually make their way to the positive through the red wire back to the positive terminal of the battery, okay? So how do we make this? So how do we use our hand rules to predict what's going to happen here? First of all, let's think about it in terms of electron flow, okay? You can do current if you want to check my work. I'm going to do electron flow. So where are electrons going to come from? They're going to come from this negative terminal, okay, into the black wire onto this section of the plate. Okay, so what should I use? Electron flow, left or right hand? should use my left hand. Okay, negative charge always gets a left hand. So the thumb in our third hand rule is the direction of the charge. So where the direction of the motion of the charge. So where are the electrons going to be coming from? They're going to go in there. Then in the portion we're interested in, perpendicular to this magnetic field that's up, right? They are going to move that way. Notice perpendicular, right? 90-degree angle. Here's the electrons moving. Here's the magnetic field up. So according to that, what is the direction of the force this wire is going to feel? So as the electrons come across this way, away from the camera, right, towards me, okay, and the magnetic field is up, according to our third hand rule, see what I mean by you can push, right? You literally push. What is the force, the magnetic force going to be? It should be pushed this way, okay? It should be pushed this way, to my right, your left, okay? Let's see if that's what happens. So if I hook this up to the negative terminal, I always do that. Look at that. Isn't that cool? So it's still hooked up. Okay, no current now because it's not completed. Right? So electrons are flowing this way. Magnetic field is up, so it gets pushed this way. What if I do it not quite as perpendicular? Well, the force is not quite as strong, right? It doesn't accelerate quite as much as we know according to Fm equals QVB, or I guess in this case it's more of an ILB situation. Okay, try using current. Let's try using our right hand rule. So where would a positive charge flow through this circuit? It would come along the red wire, right? Now it would get here, a positive charge would get here. If this wire allowed it to complete the circuit, right, it would go across that way. So in this portion here where we're interested in, with my right hand rule, now charges are coming at you. Magnetic field hasn't changed. That's still up, right? This is still the North Pole. So magnetic field's still up here. As it goes across, what does our right hand rule, if we were thinking of this in terms of current, say? It says it should be pushed that way. Should be pushed that way. Let's see, does it? Same thing, so it doesn't matter, current or electrons, as long as you're being careful with your hand rule. Okay, but that's because we're no longer dealing with current or electron flow. We are literally going to be dealing with, no, this is a positive charge or a negative charge, okay? There's not the option of thinking about it both ways. But that's not applying here yet, as you just saw, okay? Now let's think about what happens if I switch the circuit around. So now I'm going to unhook these, okay? And instead of putting black on negative and red on positive, I'm going to flip them around. But first, let's see, does the hand rule predict it correctly? So let's go back to electron flow. I'm going to switch it though, so that electrons are now going to come through the red one, because I'm going to put red on the negative terminal, right? So red is hooked up to this far side, so electrons are going to flow from here. Okay, that means now electrons are going to be flowing, so I'm going to use my left hand rule because negatives. My electrons are going to be flowing now towards you. Magnetic field is still up. So what should the direction of the force be? Wherever your palm pushes to, right? So it should be pushing off this way, pushing off this way. Okay, so the left-hand rule predicts it'll go that way. The third left-hand rule predicts it'll go that way. What about the third right-hand rule? Well, current would do the opposite. It would come at me. Magnetic field still up, and the third right-hand rule also predicts that it should go this way. It should feel a push this way. Let's see. So now I'm going to switch them up opposite way it was just a moment ago. And look at that. So does the just changing the direction that electrons are moving causes the force to be in the other direction. How cool is that? Okay, so now that we've seen that it works, let's try some examples with it and get comfortable with it. Let's just start with the first one on page 11, okay? And it asks us in this one, what is the direction of the force for all three of these? Okay, so you can probably kind of figure it out by looking at the deflection, but how can we get there on our own? Well, okay, here we have, look at that, current I, right? Current equals 0. So if I were to take the right hand rule, because it's the current, if I'm looking for the force, what is my thumb? Well, it's not moving, right? So it's kind of like this. So there is no motion, so of course there's going to be no magnetic field, right? If Fm equals I times the length of the wire that's perpendicular to B, okay, and I is 0, then of course the magnetic force is also going to be 0, right? When I had that thing hooked up, if I didn't have current running through it, the wire didn't start sliding down the thing, okay? This is a good picture too for visualizing what it means by the length of the wire that's perpendicular to the field, okay? Does this whole thing count as L? As L perpendicular? No, right? What is the length of the wire that would be perpendicular to the magnetic field? It would just be this part, right? Because it's in the magnetic field. So this whole part happens to be perpendicular, but that's also the whole part that's only in the magnetic field anyway, right? Okay, let's look at this next one. So we have current moving this way, current's going that way, okay? So current would be moving along this direction, okay? The current would be moving along that direction there through the wire, right? We have the magnetic field be in, so they told us in, but we could also figure that out by looking at the x's, okay? Now, current, left or right hand rule, we're going to use our right hand rule. And so current is positive, right? So our thumb becomes the direction of motion charge. If our fingers are the magnetic field, then into the page, okay, and thumb forward. Sure enough, my palm pushes where the force would go, so you can see I'm pushing that wire to the left. So if we ran this current, a current through this wire in this magnetic field, we would see the wire deflect to the left. Okay, finally looking at this one, now current is flowing the other way. You can see current, right? Always check if it's current or electron flow, but in this case it's current, so current is coming down. Okay, so take your right thumb, point it in the direction of the moving charge, fingers become the magnetic field. Once again, it's into the page. So when we set it up that way, with our palm points, we push in the direction that the magnetic force will cause a force, so it pushes off to the right side of the page. Okay, so this wire would deflect to the right side of the page like they've shown there. Okay, this one asks, what is the direction of the magnetic force in each case? So here I have a positive charge, okay, so that's going to be which hand rule? The right hand rule, okay. It is entering this magnetic field that is into the page, okay, and it's saying which way will the force will be. So we have our magnetic field into the page, we have our charge direction, our positive charge direction moving this way. So for our right hand rule, take your right thumb, be the charge, and then our field is into the page. So which way, what direction will the force be? It will be up towards, I shouldn't say up, it'll be towards the top of the page, right? So FM would be, let's look at this one. We've got magnetic field. It says up. It should really say towards top of the page. So magnetic field is up towards the top of the page. Careful. Now we have a negative charge. Okay, so now we have a negative charge moving that way. Okay, so negative charge going into the field at that angle. What will our magnetic force result as? Well, we take our left hand this time because it's a negative charge, make our thumb the direction of motion for the charge, so that's going to look like that. And our magnetic field is our fingers, so those point towards the top of the page. And what will our resulting force be? Well, it'll be pushing up. So this charge would deflect. This charge would deflect like this, right? It would come towards us. It would come towards us in that field. Okay, so we'd have that, and what would the resulting force look like? Resulting force would look like that coming at us. So how would we represent that on flat paper? We would draw a dot. So F. Okay, looking at C, we have the magnetic field to the right side of the page. We have a positive charge, okay, positive charge moving that way into the field. Now notice here, what is the perpendicular component of this thing's motion relative to the magnetic field? So in other words, if I have the motion this way of the positive charge and the magnetic field this way, what's the perpendicular component of that velocity relative to the magnetic field it's going to enter? Well, it's zero, right? It doesn't have a perpendicular component. It is anti-parallel, we would say, right? The angle between them would be 180, not 90, okay? So they do not have a perpendicular component. So what kind of force will this feel? This will feel no force because no perpendicular component of V. Okay, now this one. There is a perpendicular component. Is it all of the velocity? No, right? So we have a positive charge moving that way. But notice there is some component of the velocity that's going to be perpendicular to the field it's entering, right? If I have V like this, and it's entering a magnetic field like this, then the perpendicular component of its velocity would look something like that, right? Its parallel component would look like that. See how it's parallel to the field line there? Okay, and they even tell us that this angle is 45 degrees. So to get the perpendicular, if we were actually asked to do math with this, which we're not, but it helps to think about it, right? If we were actually asked to do math with this, we would have to take V sine of 45, right? That's the angle it makes with the magnetic field as it enters. V times sine of 45 to get the perpendicular component, and then we could do Fm equals QVB, right? QV perpendicular B, okay? Does this mean it doesn't experience a force? No, it just means the force is not as big. So if we're kind of going to do this with a hand rule, we would take our right hand because it's a positive charge, make that be the direction of the charge, and then notice, okay, we can put our fingers kind of off like that, and so it just is that it's not entirely perpendicular. However, it does have a perpendicular component that's just not as big, right? If I had another thumb, you could kind of say, well, there's its perpendicular component. So it does kind of have, it is going to have a force, it's just not going to be as large, right? So as we go from, if just ignore this example for a sec, as we go from here to here, right, the magnetic force goes from no magnetic force when the charged particle moves either parallel or anti-parallel, if I could twist my thumb around, to the magnetic field, right? But some magnetic force when it's somewhere in between, and then the maximum magnetic force that it could feel with that speed when it's at a 90-degree angle, okay? So yes, there will be a magnetic force. It will be in the same direction. It just won't be as large because the perpendicular component is not as large as if it were down here, right? So we have some perpendicular component. You can imagine I'm going like that and saying, okay, that's V, but then there's some V perpendicular, V parallel, right? So that's kind of what I'm saying. It's not that there's no magnetic force, it's just that it's going to be smaller than if this entire V were perpendicular. Instead, just a component of V is perpendicular. See what I mean there? All right, so anyway, still a magnetic force and still in the same direction, again, just not as large. Which way would it be? Well, positive charge, so fingers are the magnetic field, okay? This is the direction of the charge, and we see that if I line them up, then the force would be down into the page. I shouldn't say down, into the page, right? So what would the magnetic force look like? It would be an X, right? Tail feathers of an arrow, Fm into page. So again, the speed doesn't have to be entirely perpendicular to feel a magnetic force. It just has to have some component that is perpendicular. If it is entirely parallel like this, then it has no perpendicular component, and then yes, it will feel no magnetic force at all. Okay, example 4 on page 12 here. It's asking what will happen. So we got to get inside the mind of this kind of setup here. So we have a positive terminal here. Okay, we have a negative terminal here. Let's start here just for fun. Okay, what's going to leave the negative terminal? Well, electrons are going to leave that negative terminal, flow through here to get to the positive terminal. Okay, so let's do electron flow for fun. We have our negative charge then. Okay, it's saying we're interested in this scenario here because that's where there's a magnetic field and a moving charge. So if I take my left hand for electron flow, where are the electrons moving from? They're going and then they're coming kind of at us, right? Okay, so kind of at us, not worried about the magnetic field yet. And then what is the magnetic field doing? Well, a magnetic field will go from north to south, right? It'll leave north, enter south. So the magnetic field there looks like that, or up towards the top of the page. So I have my charge moving that way, my negative charge moving that way, and my fingers up. So what will the bar part of the conductor here do? It will go kind of in towards the back of this magnet, right? So Fm would be like this, towards the back of the magnet. Okay, and then again, this is a good place to think about this. I wrote down this equation, L perpendicular. Looking at this picture, can you physically see what L perpendicular is talking about? Right? So is it from here to the whole part of that wire? No, right? Because these parts of the wire from here to here and from here to here aren't in the magnetic field. So if we look at this from the side, right, you'll notice, okay, here's the south, here's the north, here's the whole kind of wire part going through, but this is not part of L perpendicular over here. Neither is this. L perpendicular is just from there to there. Okay. All right, a cool kind of practical application of this third hand rule. Okay. There are lots, but this is a cool one. We have basically a jet ski, okay, or some kind of watercraft. How does it work? Well, it shoots water backwards, okay? So use your hand rule to kind of think about how this works. Notice how it must be seawater. Why seawater? Seawater contains, what does seawater have that fresh water doesn't? It has salt in it, right? So salt. If you've taken your chemistry classes, you'll know that salt would be a solution of sodium ions and chloride ions, right? Or whatever ionic compounds, whatever salts, right? So seawater contains ions, so charges. Okay, we have electric charges in the water here. So how does this thing work? It has two, look at these, two oppositely charged parallel plates. So a little bit of chapter 11 at play here, okay? Now imagine you're a positive charge. So for example, let's say a sodium ion that's floating around in the seawater. What are you going to want to do? What are you going to want to do? You're going to want to go from that positive plate to that negative plate. So we have in here two oppositely charged plates, right? Now, a positive charge is going to want to go over to the negative. So when it enters this electric field, it's going to want to move that way. So now we're giving a positive charge of velocity towards the negative plate. It also has a magnetic field applied, so you would have a north pole down here and a south pole up here, so that the magnetic field is up. And what happens is it pushes the ions in the water out backwards, right? It pushes the ions out backwards. And then we have Newton's third law. We push the water back, push water back, and when you push the water back, what does the water do to you? Okay. Now you might be thinking, hey, I took chemistry. There's not just sodium ions in salt water, there's also chloride ions, and those are negative. Right? I agree. Take your left hand. Okay. If you're a negative charge, what are you going to want to do in this electric field? You're going to want to go that way, right? If you're a negative charge, you're going to want to do the opposite of what they've got set up here. So, okay, great. Magnetic field hasn't changed. It's still up. So what will you do? Same thing. So if you tried to take these and drive them in a freshwater lake, it would not work as well anyway, because there's nowhere near as many charged particles, as many charged ions in freshwater. You'll notice here MHD, what does that stand for? It actually stands for magnetohydrodynamic, which is a great name. It kind of breaks down all the physics. So magneto, that part's kind of obvious. There's a magnetic field. Hydro requires water, right? If you're thirsty, you need to hydrate. Dynamic, what did we study in physics 20? What was our dynamic unit all about? Forces and how they cause motion, right? So magnets, water, motion. Now, this entire concept, this entire idea that a moving charge in a conducting wire will experience a magnetic force and then cause motion is the entire reason that motors work. So this is actually often called the motor effect, right? Because this phenomenon was used to make the first motors. Okay, this was the first major application of this magnetic force that was perpendicular to the two other vectors. So how does it work? Well, it's all just hand rules. So I want you to they've used current, take your right hand, be a positive charge as you move around. Okay, so here we have a magnetic field. As always, field lines leave north, enter south. So as always, field lines leave north, enter south, right? And you can see them doing that there. Okay, on the other side, they're kind of like that. Now, if you're current, you can see, so how would we hook this up? Well, so how would this look hooked up to a battery? We would take it and hook it up to a positive terminal, always the bigger one, right? And a negative terminal, always the smaller one. Okay, that's the kind of the symbol for a battery. Bigger terminal is positive, smaller is negative. So positive charges leave, the current is going to leave. So take your right thumb, okay? So in this portion of the wire, what are you doing? You're going up or towards the top of the page. I keep saying up. Okay, you're going towards the top of the page. So your right thumb should be like that. Where should your fingers be? They should follow the field lines. So what is on this side of the wire? How is that shaft? What is the wire going to feel? What kind of magnetic force? Well, over here, right, on this side, the magnetic force will be into the page. So this thing's gonna, on this side, it's gonna kind of go like that. Okay, but now you notice the current keeps going. And then it's over here, it's coming down. It's going down or towards the bottom of the page. Okay, so now the current is going down towards the bottom of the page. So take your right hand. Okay, you've got your magnetic field, and now you're going down. So over here, what's it going to feel? Well, it's going to feel a pull out. So down here, it's feeling a push down. Up here, it's feeling a pull out. So what's going to happen if I push down on this side and pull up on this side? Well, I'm going to make it spin, right? And then eventually it gets to where now this side goes. So what do you have? You have something that's constantly spinning just by the fact that you've run a current through it and there's a magnetic field there. So you have a moving charge in a conductor causing this rotating thing. Now, if you attach that shaft to some kind of thing you want to move mechanically, there you go. You have a motor, right? So what have we done? We've taken electrical energy and we've converted it into mechanical energy. That is what a motor does. So you have electric energy and the moving charge, right? Um, ends up causing a force through this magnetic field interactions, and then that force causes motion, and there you go. Now you have kinetic energy, mechanical energy. Here is just kind of a top view. So now we're going to put our eye up here. So we're looking down on it, right? And the same idea, take your right hand rule. If you are right, so here you're looking at this part from above, you're seeing the current come at you, right? So the magnetic field fingers go that way, current's coming at you, and sure enough, you're going to feel a force that way. So this thing's going to get pushed like that over here, get pushed like that over here. Okay, then over here, it makes its way across, and then it's going down. So it makes its way across, and then it's going down away from you. So now take your right thumb, right? Keep the magnetic field still going that way, but your right thumb's now going down. What's the force? Down, right? Okay, good. That makes sense. So not only is it feeling a push up over here, it's feeling a push down over here, and so you get motion, okay? Electrical energy being converted to mechanical energy. All you got to do is hook that up to something you want to make move, right? And so same exact example here. I'll let you kind of look at this one, play with it in your mind, use your hand rules, figure out how it works. Try your left and your right hand rule, see if you can explain it both ways. Okay, so we use current on the other one. I know they've given us current here, but let's mix it up. Let's use electron flow instead. What would electrons do? They would leave this negative terminal, right? They would go up here, and then they would eventually be doing, obviously, the opposite of what a current, what a positive charge would do. So this would be E minus flow, okay? Now, in this part, electrons are going to go that way. They're going to zoop around, and then they're going to be going towards the bottom of the page that way. So now be an electron, okay? The magnetic field doesn't change because you're an electron, so it's still leaves north, enters south, okay? But take your left thumb now instead of your right, make your fingers the magnetic field, and what kind of force are you going to feel here where the electrons are going towards the top of the page? You're going to feel a magnetic force out of the page, right? A dot. So here you have that as your magnetic force. So this thing is being pulled like that, okay? Over here, what are you going to feel? Well, now you're down. Magnetic field hasn't changed. Your electron flow is down towards the bottom of the page. Magnetic field still that way towards the right of the page. So now you're pushing, your magnetic force will be down, X into the page. So sure enough, right, we have this thing being pulled towards us and pushed away from us at the same time. And so we get that motion. Okay, so sure enough, that checks out. That looks right, right, as this thing rotates like that. Okay, this is really just the same image a second later, but try this one on your own. See if you can use your hand rules and figure out, label where the force is and why it makes sense. Okay, so far, all of our applications of our brand new third hand rule have involved a moving charge that is confined to a conductor, right? Confined to a wire, so that when the magnetic force pops up, right, it moves the conductor itself. It's not just moving a single charge. It's not just acting on a free charge that is not kind of confined to a wire. So the third hand rule, it actually applies completely the same way to free charges, ones that are not confined to a wire, okay? So just to show you what that might look like, I'm going to show you a quick demonstration, okay? But then we'll come back and look at some of the more math-based analysis of this. Okay, so before I go ahead and do this from above, because that's kind of where we need to be to really look at it, I'm just going to show you the setup so you can kind of see what I'm talking about. It won't be as clear from above. So all I have here are two rulers wrapped in tinfoil, right? Tinfoil so that it is covered in metal and it conducts. So essentially what I'm going to have are two parallel plates, two conducting parallel plates. So if I hook those up to a battery, right, if I connect each parallel plate to a battery, you'll see when I hook it up what it'll look like, but I'm just going to hook each to a terminal of the battery, and that will negatively charge one plate and positively charge the other plate. So there will be an electric field between the two plates, okay? The other thing I'm going to do, I'm going to add some salt. This is leftover salt water that you can see has evaporated and crystallized a bit. So this is all just table salt, sodium chloride, okay? I've actually already added some in there, but just so you can watch me do it, I'm just sprinkling table salt in there, okay? And we'll see why when I go to it. I just wanted to show you the setup from another angle before I actually do the demo. Okay, so here's what the setup's going to look like. I'm going to unhook it. First, we're going to kind of analyze the situation with our hand rules and stuff first and kind of make some predictions, but you can just kind of see here how it's going to look once I hook it up, right? So I have the positive plate here connected to the positive terminal. Electrons are flowing from here and building up on this plate. You can actually see that bubbling. That is some that is a clear sign that electricity is being produced. So the bubbles there forming were actually hydrogen and oxygen. We were doing what's called electrolysis of water, splitting H2O into, well, H2 and O2. But that's not actually, it's not the purpose of this, okay? So I just wanted to show you the setup there. We have an electric field across. Now let's think about what's happening for each charge. So I'm just gonna move this for a sec, okay? Remember how I had it hooked up? Okay, so I had my cable that goes to my negative terminal, the black one, right? I had that hooked up to, okay, so that would be my negatively charged plate. And then I had this one hooked up, so I have my positively charged plate. So here I should have used red and black for color coding, but I've kind of been using blue for positive and red for negative, so I'll stick with that. Okay, now what did I put in the solution again? I put into there sodium chloride, right? Table salt. If you've taken chemistry at all, right, you know that sodium chloride is very soluble, and when you put it in, it will dissociate into its ions, right? Ionic compound. You all know that word from Science 10. Ionic compound meaning made up of ions, which are just charged particles. What makes up sodium chloride? Well, there's positive sodium, right? Positive sodium, and there's the negative chloride, okay? And so there are tons of those floating around in here, right? Literally billions and billions of them floating around in there. Tons of those little ions, those charged particles. Okay, so if they're charged, what are they going to want to do? Well, they're going to want to do two different things. Chapter 11, right? The chloride is going to want to go towards the positively charged plate. The sodium is going to want to go towards the negative charged plate. So what is that going to do? It's going to make them move. They're going to have some speed, right? So that will be how sodium will want to move. That will be how chloride will want to move. Okay, so that was happening when I hooked up the current. The thing is, it wasn't that interesting yet because, well, they would just kind of do that. We also can't see them. Ions in solution, right? A true solution, you can't see anything in there. It's a uniform mixture. But how could we make this a little more interesting? Well, what if I were to bring a magnetic field into the mixture? Okay, so these free charges that are floating around in solution, they're not in a conductor. I'm going to bring a magnetic field into the equation here. So I have here a fairly powerful neodymium magnet. Okay, let's take a look. Let's figure out what its north pole is and what its south pole is. Okay, so there the field is pointed towards the magnet, right? And there it's pointed away. So field lines should enter south. So that must be south and leave north. Okay, so that's north. So I'm going to put it north side up. So what do the field lines look like? Well, we use our compass to check, right? They are coming at us. So if I put this, I'm going to put this underneath my whole setup so that, right, I'm going to sit this on top of the magnet so that then what do the field lines look like? The magnetic field lines. Well, they are like all other magnetic field lines. They're leaving the North Pole, right? Yes, they're going to loop around back to the South Pole, but where they're strongest, they're going to be leaving the North Pole, where they're the strongest for our apparatus, right? They're very strongly leaving out. Right here, quite strong, okay? They are coming up out of the plane. They're coming out of the plane of the board right at us where I'm going to actually look, okay? So I'm going to do a test to see what's happening at this point. I'm just drawing these over here to give myself some room to draw everything. Okay, now ask yourself, if you're a positive ion, if you're a positive charge, you've been given a speed because of the electric field, right? You have motion because of the electric field. If there's a magnetic field there as well, will you feel a force? So are you perpendicular to this magnetic field? Well, the magnetic field is out of the plane, right, of the page. Your velocity looks like this. So yeah, it is perpendicular, right? 90 degrees. As we know, if there's an external magnetic field and a moving charge with a perpendicular component to that magnetic field, then it will experience a magnetic force. Now, positive charge, which hand rule? Use your right hand rule for a positive charge. Okay, the magnetic field is coming out of the plane of the page at you, and the charges should be moving this way. Okay, I have to bend my thumb a bit. So which way should it feel a force? Its magnetic force should feel a magnetic force this way, right? So it should, the initial first kind of push that it feels from this motion should be that way, right? That should be kind of the first thing it feels. Okay, and we'll get to what it keeps doing after that, but just right off the bat, initially it's going to feel a deflection, a deflective force that way, right? What about the chloride ion? Well, left hand rule, and it's also moving the other way, but the magnetic field hasn't changed, so what does it feel? Aha, it actually feels the same thing, right? It actually feels a force in the same direction towards the left side of the board here. So same thing goes for chloride. Okay, so what that means then is that we have all of these ions, whether they're positive or negative, that are floating around in here, right? All of them are feeling that magnetic deflective force to the left. Now, well, if I hook it up, they will be, okay? Or they should be according to our hand rule. Now, how can we see that? Well, we kind of can't, right? We can't see the ions moving. However, if all of those ions are moving, they are kind of going to be creating a bit of a current, a bit of a pull. That's actually how a lot of currents in the ocean come from. They come from salt ions moving from places of high concentration to places of low concentration. So we should get a bit of a current at that point. So if I were to sort of color the water there, we might be able to analyze how the ions are moving within the solution because of that magnetic force. Okay, so there we go, two parallel oppositely charged plates with a magnetic field coming out of the plane of the page and a bunch of ions to move around. I'm going to drop in a little bit of food coloring and we'll see what happens. Notice which way it's all kind of going. There's a little bit of a current going on here. And normally when you drop food coloring into water, it spreads out pretty quick, right? It diffuses around. Notice it's all kind of sticking over there to the left. You can see that. Oh, wow. Do you see that? Look at that current down there as it goes. There's an immediate kind of whoosh pull. So the ions, as we saw with our hand rule, are all being pushed that way. And as those ions flow through the water that way, they kind of create a current that way. Why are they all flowing that way? Well, just a magnetic force. That is so cool. Okay, so when a free moving charge enters a magnetic field perpendicular to the field, okay, so when a free moving charge enters a magnetic field, it is not going to stay within that wire. If it's not in a wire, if it's just a free, for example, an electron flying through or a proton flying through or an oxygen ion or whatever flying through, it can be, there's not a wire that it's stuck in. So it's able to move. Its trajectory can be changed, right? And it says the force there. What kind of force? What are we talking about? We're talking about Fm, right? The magnetic force, okay? It can change its trajectory. Will it? It will, as long as as long as V has a perpendicular component to B, the magnetic field, right? Okay, so the example 1 there asks us, kind of using the ones below, what type of motion are we looking at? Okay, so to figure that out, let's use our hand rules and think about what's going on here. So in the first one on the left-hand side there, we have a positive charge, okay? A positive charge entering a magnetic field that it is indeed perpendicular to. Okay, so there's our perpendicular magnetic field. And they've drawn the force in for us, but let's see how they got that. So they had a positive charge, okay, right hand rule, entering a magnetic field that leaves north, enters south, so that goes like that. And notice, okay, at first, what kind of force is it going to feel? First, it's going to feel a force up. Okay, great. But then it's going to accelerate up, right? As you push it up, it's going to change its motion up. Okay, great. Now its velocity, right? Now its velocity is still perpendicular to the field, right? And so, but the magnetic field hasn't changed. So you're going to feel a force kind of this way now, right? Now that its velocity has a bit of an upward component, magnetic field hasn't changed. Notice how the force is kind of curving, right? So the force is now inward a little bit more, right? Now it's that way. If you're saying to yourself right now, but hang on, it's not perpendicular to the field if it's moving up. Be careful, right? Well, let's think about this carefully, okay? So let's just say, obviously kind of not really from this perspective, but let's say our velocity goes like that, okay? And our force goes up, and let's say our magnetic field kind of goes away from us like that. Okay with that? Okay, so our magnetic field kind of goes like that. All right, so we're saying that this force is going to cause the velocity to change upward. It's going to make it accelerate, right? A force can cause an acceleration. What's an acceleration? It's just the rate of change of the velocity. So if there's an upward force, there'll be an upward acceleration, which means the velocity is going to gain more and more kind of upward components. Now notice, as I make this go more and more and more and more up, or even all the way up, does that ever change the perpendicularity, okay, of the velocity to the magnetic field that it's traveling through? No, right? I can go all the way around, and at no point is the angle here no longer 90 degrees. The velocity can go all the way around, and at no point does it end up not being at 90 degrees to that magnetic field. So the force, that magnetic force, doesn't disappear because, yes, it's changing its motion, but it's changing its motion in this plane, which is that plane, its entire plane of motion here. Do you see they've even kind of highlighted it? It looks like a frame of glass. That entire plane is perpendicular to the magnetic field. Okay, let's look at the next one. On this one, we have, what kind of charge is this? Is it positive or negative? They actually don't tell us. Let's figure it out. So we have magnetic field lines leaving north, going to south. Okay, I'm going to use this point here just to think about. If this is a negative charge, let's try that. So if it's negative, either way, the magnetic field is down that way. My hand would be going that way, which would say the force should be out towards the page. Nope, that doesn't make sense, because how could this thing be pushed? How could this thing's velocity be kind of changed inward if the force was outward like that? So that can't be right. This must be a positive charge. So whatever this thing is, it is a positive charge. Okay, positive charge. Now notice, take your right hand, go all the way around. Notice, since the force is in, its velocity is constantly going to be kind of changing in a bit, right? So the velocity is kind of changing in, and the force is always going to be changing with that velocity. So since there's an inward force, as soon as that velocity changes, so too does the force, kind of by our right hand rule, right? So you're kind of scooping it around like that. If we were to view it from above, what would we see? We would see it go like that. The force kind of always keeping it in. This force, notice it's always kind of center seeking. It's always causing this thing to accelerate in towards the center. Hey, does this sound familiar from Physics 20? What kind of motion is this? This is circular motion, right? This is uniform circular motion. There is a centripetal force. In this case, it is the magnetic force. It's a center-seeking force. It's constantly radially inward by our right hand or left hand rule, right? As the velocity changes, so too does the force, and vice versa. The force is causing the velocity to change in the first place. Notice, the perpendicularity thing is not broken here. At every point, the velocity is still perpendicular to the magnetic field, and it's perpendicular to the force, and same goes for the force. The force is perpendicular to the magnetic field and perpendicular to the velocity, right? Because this entire plane here, this entire plane that this circle exists in, is perpendicular to that magnetic field, right? That whole plane there, that whole flat circular area is perpendicular there. So everywhere in there, the velocity is still perpendicular as it's changing. Okay, so what type of motion is this? As we saw there, right, with our hand rule, this is going to cause circular motion. So circular. Okay, so this is a physics principle. Uniform circular motion is a physics principle. If you flip over the back of your data sheet to get the number, it's one you haven't really used since Physics 20 until today. That is physics principle 2. Okay, so remember when we were doing electric fields? Let's just, again, remind ourselves. Remember when we were doing electric fields and we had a positive plate and we had a negative plate and a charged particle entered? What did we say the path would look like? We said it would be parabolic, right? Or parabola shaped, because at no point along there is there any x direction force, right? It's going to get pulled towards the negative plate. There's only ever a y force, right? There's nothing in the x-axis to actually make it change its motion in the x-axis. Now we are in a perpendicular magnetic field. So that is actually no longer the case, right? If I take some particle and I send it in there, okay? If I take some particle and I send it in there, at that point, let's just say this thing is negative, for example, an electron. Well, now this thing does have, at that point, it feels, sure, initially it only feels a y force. The Fm at that point, if you use your hand rule, would be down, right? But again, now there is an x component because all that has to do, all that Fm is perpendicular to the velocity. So as the force causes a change in the velocity, it's kind of also causing a change in itself because it's perpendicular to the v, right? It's kind of a self-feeding cycle here. F changes v, which changes F, which changes v, which changes F, so that eternally they're kind of, so that they're going like that, right? F is always radially inward. Okay, just like when you had a ball on a string and you were whipping it around in physics 20, right? If you were twirling this around, the tension in radially inward was called a centripetal force, right? A center-seeking force, which was causing the velocity to change. It was always tangential, right? Same thing here. The velocity is always tangential, but it is constantly changing, right? It is always, the velocity is tangential, but it's constantly being accelerated inward by this center-seeking force. You might remember in gravity, same thing went for gravity, right? Why do the astronauts on the space station float? Not because there's no gravity out there. If you do Fg equals gmm squared where the space station is at, you're going to get pretty close to 9.81. Okay, it's not that different. Okay, the reason is that they are constantly kind of going sideways. They're just going side, and they're constantly kind of falling. Gravity is constantly accelerating them towards Earth. They just have enough sideways motion to always miss the Earth as they're falling. Okay, so just a bit of a quick crash course reminder on circular motion. The force is causing the velocity to curve inward, which causes the force to curve inward, which causes the velocity to curve inward, so that we get this centripetal force. Okay, so it asks us to derive the equation to determine the magnitude of the magnetic field if we have some information here. So, well, we know that the magnetic force now, okay, is equal to something we haven't seen in a little bit, but it is now a centripetal force. The magnetic force is a centripetal force when we have this kind of motion. Okay, we have a couple equations. MFM. Well, this is a free charge, so it's going to make the most sense for us to use Q V perpendicular. The charge's perpendicular component of its velocity to the magnetic field, and then that magnetic field. Okay, QVB is equal to FC. Remember what FC is? Well, every F is an MA, right? Every F is an MA. So centripetal forces is just mass times the centripetal acceleration. Now, this equation isn't actually on your formula sheet. However, this one is. This one is. Okay? The centripetal acceleration is equal to the velocity, the tangential velocity squared over r. The tangential velocity, since at all points on this circle is perpendicular, right? Then v here is actually the same thing as v here. Okay, so let's just rewrite this then. So qv perpendicular times the magnetic field is equal to m. Now AC is going to be mv squared over r. Remember this? FC equals mv squared over r. You getting flashbacks to physics 20? Okay, there we go. So now, what did it ask me to do? It asked me to derive an equation to determine the magnitude of the magnetic field. So let's just divide both sides by QV perpendicular, QV perpendicular, okay? And so we're given that the magnitude of the magnetic field is equal to, okay, mv squared over rq v perpendicular. And again, v and v perpendicular are the same thing here, right? V is always perpendicular, okay? At least the ones we're going to analyze. It's possible for it not to be, but we won't have to analyze those. You can read your textbook if you'd like to see what they look like. For now, in the interest of time, we're not going to worry about it. But v squared over v, that's the same thing. So squared and v are gone. And so the magnetic field strength, the magnitude of it is equal to mv over qr. So the mass of the particle entering, the velocity at which it entered, the charge of the particle, and the radius. Hey, look, we can actually, if we know our magnetic field strength, we know the velocity it entered at, by just measuring something's radius of curvature, we can actually figure out what kind of particle it is, right? This is actually something that is often used to determine particles that are flying through space. For example, I know at the University of Alberta, they have a big, and it's not even like a big piece of research equipment, it's just kind of something cool you can stop in and look at in their physics building, right? Is it's called a bubble chamber. So it's essentially what it is you look at it and you constantly just kind of see these little spirals that come in, right? And by looking at the radius of the curvature that it follows, okay, looking at the knowing the magnetic field strength, because you kind of set that, well, then you can figure out the mass to charge ratio, charge to mass ratio, and actually then figure out what particle it is. Pretty cool. Okay, so we have a magnetic field is directed into the page. So why am I drawing X's? Well, those are the tail feathers of the magnetic field as it goes into the page. Okay, so there's a magnetic field. Now, particles fly in from the left. Describe the motion if the particle is an A electron. So let's do A. If I have an electron and it flies in from the left, let's assume they all fly in at about the same speed. Okay, it flies in from the left. So that's its kind of V to start with. What is its path going to look like? Well, it's negative, so we'll use our left hand rule. Okay, thumb is the direction of motion of the particle. So thumb is the motion of the speed of the particle. Fingers are the magnetic field. Where's the magnetic field? Well, it's into the page. So what kind of force is it going to feel? It's going to feel a downward force at first, right? At first it feels that downward force. But then its V changes a bit like this. So now the force is a little bit like that. Then the V changes again. It's a little bit like that. The V gets changed a little bit more. It's like that. The V actually gets changed so much that eventually it's up, the opposite of where it started, right? And then it kind of keeps changing and it's in, it's in, it's in. And what do we have now? We have circular motion, right? This is no different than a ball on a string, right? If I swing a ball on a string, the tension in the string constantly pulls it back in, constantly causes the V to change so that the force is always inward and the ball is always technically accelerating inward, right? Or a planet orbiting something else where the force of gravity is the centripetal force. Now the magnetic force is the centripetal force, okay? So what will this thing do? It will come in, it will, right, constantly feel a force in like this, right? At initially that will be FM and then that will be FM and then that will be FM, always perpendicular to both the magnetic field and the V, right? And eventually this thing will enter circular motion, the path looking something like that, okay? Now we're going to have to, now that the first one, okay, sure, we can draw it kind of however we want as long as we curl it right. We're going to have to think about how the next ones are going to compare. So what about a proton? So be a proton. Okay, so a proton is going to enter this magnetic field. And what's it going to do? Well, which hand rule? Right, for the positive charge. Okay, great. So it's going to come in. Now, it is going to feel a force upward instead of, or towards the top of the board instead of towards the bottom of the board, unlike the electron, right? Now let's think about what does the path of the charge depend on, or the particle depend on while it's in the field. So I'm just going to remind ourselves, Fm equals Q V, and we assume they all are going to have about the same V, times the strength of magnetic field. Well, they're all going through the same magnetic field. Okay, so between an electron and a proton, are they going to feel any different kind of magnetic force? No, right? They should feel the same magnetic force. Okay, great. But will that force affect them both the same? So remember, Fm, right? The centripetal force is going to equal the magnetic force. And what is a centripetal force? Well, it's the mass times the centripetal acceleration, right? Which is, well, it's mv squared over r, right? So mv squared over r equals qvb. So when we're drawing the path, what are we really needing to think about? We're really needing to think about r, right? When I go to make proton, the p, I know it's going to go up, but is it going to go up faster? Is it going to go up slower? Well, let's just kind of see the dependency. Let's just see what r really depends on, okay? So if I, just because that's really what we're interested in here, right? R, if I bring it up here and then divide both sides by QVB, and then I have V squared over V. Okay, so R depends on the mass, the speed at which it enters, which you said is going to be constant, the charge, and the magnetic field, which is also going to be constant. Okay, so between an electron and a proton, the charge does not change, right? However, the mass changes a lot, right? The mass changes a lot. You can even think, yes, this is nice to have now, but think about F equals ma, right? Is this proton's acceleration going to be the same? Of course not, right? Its mass is, a proton is about 1,800 times more heavy than an electron, or more massive, I should say, than an electron, right? So its path is definitely going to be, well, let's see. If I make the mass bigger, right? If I make this number bigger, what happens to the radius of curvature? Well, if I make m bigger, so r gets a lot bigger too, right? Well, that makes sense. If it's way heavier, the same force isn't going to affect its motion as much. So it's going to, this is not to scale, by the way, but it'll do something like that. The circle will be a lot bigger if this magnetic field is even big enough to, right, for it to not escape and end up doing its own thing. See, an alpha particle. What is an alpha particle? Again, and it's just a helium nucleus, right? So essentially, take a helium atom, kick off the electrons, you got 2 protons, 2 neutrons. However, that does not weigh the same as 2 protons and 2 neutrons. We'll get to that in our last unit, okay? But for now, C, alpha particle is on the mass of an alpha particle is on the back of your periodic table. It is 6.65 times 10 to the negative 27 kilograms. All we super need to know right now, because we're just kind of getting a feel for these concepts, is that compared to the proton, its mass is bigger, right? Its mass is bigger. That's alpha for alpha particle, okay? Its mass is bigger about 6. Its mass is bigger than a proton, about 4 times bigger mass. Don't forget though, right? The charge of an alpha particle is plus 2e because there's 2 protons in there. So the charge, and again, that's on the back of your periodic table. So it's plus 2 times the charge of a proton. So so yes, the radius of curvature will be bigger, but it's not going to be 4 times bigger. It'll be 4 over 2 or twice as big, right? So let's draw it bigger, the radius bigger, but not 4 times bigger. So roughly, maybe something like that. Okay, but I forgot to use my hand rule there. That was the whole point. Y still up, it's a positive charge, so right hand, okay, it's moving that way. Magnetic field is still into the plane, so just ever so slightly getting. The force is actually bigger here, right? It's double the force, however, it's 4 times the mass, so it works out to half the acceleration and therefore half the radius, okay? But just getting pushed there. Okay, let's look at D, a neutron. D, a neutron. Okay, so yes, according to this equation, what's the charge of a neutron? 0. So R goes to infinity, right? Do you know what a circle with a radius of curvature of infinity looks like? It's kind of a silly question at first, right? But it actually kind of does exist. A circle with a radius of curvature of infinity actually is a straight line. We'll get there without having to think of it that way, though, right? Remember, don't get lost in this equation. This is helpful when we're looking at stuff that is going to curve, but how do you get a magnetic force? Fm equals QVB. Hey, if Q is 0, what's F? 0, right? Okay, so as this particle, first of all, which hand rule do you use? You kind of can't use either one. There's a clue too, right? It's not negative, it's not positive. So if there's no hand rule to be used, there's a good clue, okay? Now, a neutron will not experience any force. So will it deflect up? Will it deflect down? Nope. What will the path of a neutron look like? And that goes for any neutral particle, right? You must have a charge to feel a magnetic force in a perpendicular field. Okay, sorry, you are going to see a few things. You are going to see all the math here kind of worked out while I'm still talking about setting up the scenario. And then you are going to see once later when I'm working out the math, you're going to see a different picture up here. That's because I did not read very carefully and I did the whole problem at first as if it was an electron. And at the end, when I was about to put in my numbers, I realized it was never an electron. It was supposed to be an alpha particle. So I had to go back, fix my picture. And then, so that's why you'll kind of see it change. That's just why you're seeing stuff out of order, sort of. Okay, so let's actually try to do some calculations with this now, some hard calculation. Well, okay, so let's actually try to do some calculations with this now. So example 3, an alpha particle is accelerating to 0.85 c. Remember c, the speed of light on the back of your periodic or your data sheet. Taught too much chemistry recently. To the right, when it enters a perpendicular magnetic field, a perpendicular magnetic field of 1.2 Tesla into the plane of the page. What will be the direction and radius of curvature of the path? I'm just going to take out that word direction because what's the direction of a radius? There are times in your physics and in your math, you will think of radius as having a direction, but realistically for us, the radius is exactly what it sounds like. It's half of the circular path that it's going to take. If you wanted to give it a direction, you could say it's radially inward. I'm not really going to do that here though. So let's just find how big the radius of curvature will be. What we will do is conceptualize the direction that it will move, right? Will it move counterclockwise or clockwise? That's what. First, let's draw it so we can figure that out. So it's accelerating to the right when it enters a perpendicular magnetic. So there's our magnetic field into the page. I'm going to draw our alpha particle over here. Okay, and our alpha particle is moving to the right with some v, okay, with some v, which we know is 85% the speed of light by the time it gets there, okay? First things first, which way is the initial force that it's going to feel, the initial magnetic force once it enters this field? So left-hand rule or right-hand rule? Well, an alpha particle, remember, an alpha particle has a charge of plus 2e. Okay, that's on the back of your formula sheet, which makes sense. It's just a helium nucleus. So it has the same charge as 2 protons, right? The 2 protons in a helium nucleus. So it has a positive charge. So this is going to be our right hand rule, the third hand rule, right hand version, right? Because it's entering a perpendicular magnetic field and we're trying to figure out the force that it will feel. So as it enters, okay, if you take your right hand, I want you to try this, follow along, take your right thumb, and that will be the direction of particle motion. Then take your fingers, point those in the direction of the magnetic field. So right now your finger should be pointing into the screen and your right thumb should be pointing to the right of the screen. And what does that mean your hand is doing? Well, it's pointing up towards the top of the screen, right? So you kind of would be holding out your hand like you're asking for money or something, okay? So the magnetic force at that point would be what your palm is trying to push it, right? So up, that would be Fm. Now initially it would be up, yep, but now follow along, take your, okay, but now follow along, take your hand. That force up is going to cause this V to change. And if the V changes, that means your thumb needs to change. And then how do you change your thumb without changing where your palm is, right? So again, a force up is going to cause it to accelerate up. So its velocity is going to change to be more up, right? Okay, but now follow along with your right hand. We're going to have that push. What does a force cause? Well, it causes an acceleration. So it's going to cause the velocity to change to be more upward. Now, as that velocity is changing to be more upward, right? What does that mean for our hand rule? That means your thumb is going to be shifting upward. Now, you can't shift your thumb and keep it perpendicular without also shifting your palm, right? So that means the force is also kind of changing. It's going more in. So the force is going to get more and more left and left, and then it's going to get more and more down and down and down, and then it's actually going to get right and right and right until, right, we've kind of ended up right back where we started, where we have a velocity that is to the right. So why is that happening? Again, because as you move your thumb, you will see your palm is also changing, right? So at each point, because the force is perpendicular to the velocity, you can see it kind of, it's a center seeking, it's a centripetal force. And so once we have this circular path, what are we looking for? We're looking for what is the radius of that circle, right? So r equals question mark. Okay. Let's go ahead and actually figure out what the radius is going to be. So what kind of motion do we have here? We have circular motion, right? So we have Fc, okay, equals, what is the centripetal force here? Well, the centripetal force is, as you can see, right, at every point, the center seeking force is the magnetic force. So Fc equals Fm, okay? And then we just have to think about the expressions we have for both of those things and solve for our notes. So Fc is going to be, always, this has not changed since physics 20, mv squared over r, which again is just m times ac. So Fc equals mv squared over r is not on your formula sheet, but F equals ma is, and ac equals v squared over r is. So it kind of is on your formula sheet if you can put it together. Okay, equals Fm. This is a free charge, so it makes the most sense to use Q V perpendicular, which in this case is all of V, right? All of V is perpendicular to the field, so we're good there. We can just use that V perpendicular equals V. All right, so what are we looking for? We're looking for R, right? We're looking for R, so let's just multiply both sides by R, and then we can divide both sides by QVB. So we will have, in the end, okay, R equals mv squared over qv magnitude of B, okay? Do some cancellation because this V, right, is the V of the electron, right? It's the, yes, it's the tangential velocity, but that's just the same velocity it entered with. It's just being caused to move in a circle. Okay, so V squared over V, same V, see you later. That means R equals mv over qb. We already kind of derived this, but it doesn't hurt to do it again. Okay, so then just plug in. Okay, so the radius of curvature then is equal to the mass of an alpha particle. So on the back of your formula sheet, the mass of an alpha particle is 6.65 times 10 to the negative 27 kilograms. Okay, E is the 85% the speed of light, so 0.85 times 3 times 10 to the 8 meters per second. Okay, all divided by QB. What's the charge of an alpha particle? Well, it's 2e, or 2 times 1.6 times 10 to the negative 19 coulombs. And B, we were told, is 1.2 Tesla. Okay, quick unit analysis here. For the unit analysis, I'm just going to say, hey, remember what a Tesla is? It's a kilogram per coulomb second. I'm just going to kind of write that below so we can do our cancellations here. So kilograms over kilograms, nice. Okay, those are gone. 1 over seconds over 1 over seconds, those are gone. Then we have coulombs times 1 over coulombs, those are gone. What are we left with? Just meters, which means essentially Teslas are gone, right? If kilograms per coulomb second, Teslas are gone, leaving us with just meters. Hey, what are the units of a radius, of a distance? That is a meter. So R equals, if you punch that all in your calculator, I got 4.4 meters. Now we kind of already, without even doing any math, we kind of already determined this thing's path direction, right? What is its path direction? Well, clockwise or counterclockwise from our perspective, right? That would be the opposite way a clock goes. So 4.4 meters, counterclockwise motion. Here's one that brings in some of chapter 11, okay? So an electron is initially moving south at 1,000 kilometers per second when it passes two parallel plates with 2,000 volts difference between them. So 2,000 volts of potential difference between them. In other words, as it passes through those plates, it's either going to gain or lose 2,000 joules per coulomb of potential energy. So the accelerated electron, it's going to either gain or lose 2,000 joules per coulomb of potential energy. And gaining or losing 2,000 joules of potential energy is the same as losing or gaining 2,000 joules of kinetic energy, right? Okay, so the accelerated electron enters a perpendicular magnetic field and moves clockwise with a diameter of 4.5 centimeters. Careful, that's tricky. That's a mean trick. Diameter of 4.5 centimeters. Useful, but don't forget R equals D over 2. So in this case, that would be 2.25 centimeters, right? D does not appear, diameter does not appear in our equations, radius does. So we're trying to figure out what is the magnitude and direction of the field. Okay, so we have to make an assumption here. It says accelerated electron, but remember, being slowed down or being sped up is accelerating. So let's go ahead and say that this field is going to make the electron go faster. Okay, so let's just try and visualize this here for a sec. We're going to have it's going to be able to pass through some plates. Truthfully, this setup kind of wouldn't work the way we're drawing it, but just to allow the electron to actually pass through. It has a VI here, so let's pretend this is south over here just to make it easier to draw. So VI equals 1,000 kilometers per second, which is 1,000 times 1,000, or 1,000,000 meters per second, right? Going this way. So if this thing's going to get accelerated, which way is the electric field? Well, remember, defined as what a positive charge would do. So there's our electric field. And also, it's going to speed up our electron, we said. So that makes sense. It should be against the electron's motion because, right, an electron will do the opposite of what the electric field kind of direction is because it's negative. Okay, so the electron's going to go through there. It's going to get sped up. Then whatever V it ends up with here, right, at the end is going to be the V that it enters some magnetic field with. Okay, so it enters some magnetic field. We can't draw the magnetic field yet because one of the whole points of the question is to figure out what the direction of the field is. So first, let's just draw the path and then we can kind of backwards think to what the field direction must be. So it enters a perpendicular magnetic field with some V, which is really the VF from here. Okay, so the VF after passing through. Okay, so V, we don't know it, but it's going to be the VF from there. We can even call it VF if we want. Okay, so VF, and then it enters this magnetic field and moves clockwise. So it now moves clockwise. Okay, so So how does a clock move? Well, it goes to 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, 6 o'clock, blah, blah, blah. Okay, that's kind of what its path is going to look like. And it does that with a diameter of 4.5 centimeters. Don't fall for that trick. That means we're interested in the radius, which is 2.25 centimeters. Okay, great. So take the appropriate hand out. Okay, is it going to be your left or your right? Now point that hand, the thumb of it, right, the way you should, and think about the force that this thing felt, and what do you get for your magnetic field lines? Well, when I'm doing it, I'm getting that my thumb, my left thumb is pointing to the right of the screen. My palm, initially, the direction of the force should be down to get this kind of path, right? And then as we go, it kind of gets pushed in along the way, pushed, just kind of squeezed in the whole way around, okay? So what do your fingers need to be like for that to be the case? I don't know about you, but I'm getting that my fingers would need to be into the page. Okay, so there we go. We already answered the direction just with our hand rule. They would need to, the magnetic field would be into the plane of the page. Okay, now to get the magnitude of the electron, we know that the magnetic force equals the charge times the perpendicular component of its velocity, which again is just going to be the whole velocity this time, times the magnetic field. And we know that since magnetic fields, if it's perpendicular, causes circular motion, we know that, well then, mv squared over r equals qvb, okay? And so since we're looking for b, we'll divide both sides by qv. And again, that's the same v, so let's just go ahead and do that now. So then our magnetic field equals mv over qr. Okay, great. We got r. We know q for an electron. Okay, we know the mass of an electron. Those are on our periodic table. Problem, we don't know v, right? Because really that's this v. That's vf, right? That's vf. Okay, but if this was chapter 11, right, you've done this problem quite a few times. If it enters with this speed into some electric field with a known potential difference and you know the object's charge, can you figure out its change in kinetic energy and therefore its change in speed? Yes, you absolutely can. Okay, so our mission now is to find v, okay, so that we can plug it in there. So find vf, we can call it if we like, okay, which is really just the v that it enters with, which of course is v perpendicular. Okay, so how would we do that? Well, we know that the potential difference, the voltage, is equal to a change in potential energy divided by the charge of the object traveling through the potential difference. In other words, joules per coulomb, right? The definition of voltage. Okay, change in potential energy. Why? What is potential energy changing into? Well, in terms of magnitude, that is equal to the kinetic energy, right? Because all that potential energy is not disappearing, it's becoming kinetic energy. So mathematically, that is true. Change in kinetic energy is just EKF, what it ended up with, minus what it started with, EKI, divided by charge still, which of course, EKF is equal to MVF squared over 2 minus MVI squared over 2. That's just the numerator divided by the charge. So let's think about it. Do we have everything we need? What are we looking for? We're looking for VF. Got M, right? Know the mass of an electron. Got VI, they gave us that. Got the charge of an electron, and we have the voltage. So this is solvable. I'm just going to move it around a bit. Okay, so let's multiply both sides by Q. So we have, right, multiply both sides by Q. Okay. Looks weird because there's a whole bunch of middle stuff, but don't let that bug you. So we have Q times the potential difference is equal to mVF squared over 2 minus mVI squared over 2. Okay, you could manipulate this in a totally different way. I'm just going to make my life a bit easier here and make it a few less steps. Let's just pull out, notice, M and M, those are the same, right? It's both the mass of the electron, of course, over 2, that's the same. So this is essentially, right, it's the same as M over 2. If I pull that out as a common factor, VF squared minus VI squared. Okay, if you're not okay with that, just go ahead and add this to both sides and then do it the usual way. I'm just going to do that because it's going to save me a little bit of time. Honestly, not that much time. Okay, so Q delta V equals M over 2 times VF squared minus VI squared over 2. Don't forget, what am I trying to do here? I'm trying to get VF squared. So first, I need to get rid of everything outside the bracket. So let's just multiply this whole side by, okay, 2 over M. 2 over M. You see what I'm doing there? By multiplying by 2, I cancel that out. And then by multiplying by 1 over M, I cancel that out. Can't multiply that side by 2 over m without multiplying this side by 2 over m. There we go. Okay, let's just rewrite what I got. So 2q times the potential difference over m, right? Just multiplying that over that, equals Vf squared minus Vi squared. Now, what's happening to Vf squared? Why isn't it alone? My Vi squared is being subtracted from it, so the opposite of that is adding Vi squared. Add Vi squared, okay? And then we got Vf squared, just bringing this to the left side, equals 2 times the charge times the potential difference, all over the mass, plus Vi squared. And don't forget, we didn't want Vf squared, we wanted Vf. So square root both sides, the whole thing, you're going to square root that whole thing. Do not make the mistake of saying, oh, Vi squared and the whole thing's being square rooted, so I can cancel out that square. No, only if just Vi squared is being square rooted. This whole term is being square rooted. Okay, you wouldn't do it in math, don't do it in physics. So Vf equals the square root of 2q times the potential difference over m plus Vi squared. We know all that stuff. We can solve this. So Vf equals the square root of 2 times the charge of an electron is 2 times the magnitude of the charge of an electron is E, right? The elementary charge. Okay, the potential difference was given as 2,000 volts or joules per coulomb divided by the mass of an electron on the back of your formula sheet is 9.11 times 10 to the negative 31 kilograms plus Vi squared. Vi was 10 to the 6 meters per second, right? Just 1,000 kilometers times 1,000 meters in every second for a million. Okay, don't forget that's squared. The whole thing is square rooted. And if you put that all in very, 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 very carefully, you should get that Vf equals 26524,040 or 26,524,040 meters per second, which is a big number, but not faster than the speed of light, so we're okay, right? If you get something bigger than the speed of light, something went wrong, or whoever made the question was not very careful about the numbers, but you should never get something faster than the speed of light. Okay, anyway, here we go. We have Vf. Why did we find Vf? Let's remind ourselves. What was our plan of attack here? We found Vf so that we could put it in here, right? Because we know the radius of curvature. We want to know the magnetic field strength. We know the mass, right? We know the charge. The only missing thing was the velocity at which it entered to produce such a radius of curvature so that we could figure out how strong the magnetic field must have been. Quick unit check, and this is the perfect time to do unit checks, is when you've done a lot of manipulation like this and you're hoping, oh boy, I hope I didn't make a mistake somewhere along the way. Well, don't just hope. If you got time, check. And if your units work out, you probably did okay, okay? So just going to do off to the side. We have coulombs times volts, okay? Coulombs times volts over kilograms, and then that's being added, which doesn't change the units, but added to meters squared per second squared, okay? Because those meters and seconds are being squared. Okay, so then we have coulomb volts. What's a volt again? In standard units, it's a joule per coulomb. So we have a coulomb times a joule per coulomb over a kilogram plus a meter squared per second squared. Okay, so coulombs. Now we have a joule per kilogram, meter squared per second squared. Okay, so kilogram. What's a joule? It's well, the easiest way for me to remember it is that energy kinetic is mv squared. So it's a kilogram meter squared per second squared over a kilogram. Okay, this is looking good. The kilograms cancel, and look at what we're left with. Meters squared per second squared plus meters squared per second squared. That's not going to change anything, right? That doesn't change the units. If you have 2 meters and you add a meter, you have 3 meters. The units don't change. Don't forget, this whole thing, right, which I really should have been doing from the beginning, was being square rooted. So we have the square root of meters squared per second squared. What's that? Meters per second. Our units check out. Okay, so when you do a whole bunch of manipulation like that, that's the perfect time to lean back on your units, have them check your work for you. Okay, so let's just say unit check. So going back to this, we already manipulated for this, so I won't do it again. Magnetic field strength is equal to mv over qr, vf, I guess, right? Even though it's the velocity it enters the magnetic field with, it's the vf of the plates, equals the mass of an electron, 9.11 times 10 to the negative 31 kilograms. Vf we just found to be 26524,040 meters per second, all divided by 1.6 times 10 to the negative 19 coulombs, the charge of an electron. times the radius of curvature it had, which be careful, was not the diameter of 4.5 centimeters. It's half that, so 0.0225 meters. Okay, and when you do that, I got that. It is equal to 0.0067 Tesla. Okay, quick unit check. Meters over meters. Quick unit check, meters over meters. Cancel. Kilograms over seconds over coulombs. So kilograms over coulomb seconds. Hey, that is a Tesla. That's good. Kind of my advice, most of this stuff, honestly, boils down to setting FC equal to FM. Yeah, sometimes there might be some weird stuff where you got to figure out the V, but most of this stuff is that the centripetal force is the magnetic force, right? And you have some equations for both. We're kind of going to be revisiting current carrying conductors, so charges within a conducting wire in an external magnetic field. But now we're going to revisit it with a more mathematical approach, which we hadn't really done before. Okay, so we'll get right into it. Okay, so like I said, kind of nothing new in terms of concepts here, just a return to a charge moving through a perpendicular magnetic field, and that charge just so happens to be confined to a wire, but we haven't really jumped in and used any equations with that scenario yet. So that's what this topic will be about. So we have this equation that we looked at and actually haven't used too much. So we have that the magnetic force is equal to I, the current, right, times the length of the wire that is perpendicular to the magnetic field it enters, okay? Now, important to note, yes, the length of it that's perpendicular, but it might seem obvious, but it still goes worth saying, the length of the wire that's perpendicular, but also must be inside the magnetic field, okay? You can have all the wire in the world outside of it that's perpendicular. It doesn't matter if it's not within the magnetic field. So only inside and perpendicular to our magnetic field. So just a kind of quick note on length versus width. Length usually applies if you go along the length of something, you're kind of going along the direction of travel or the vector of it, right? So like the length of a wire, we would usually say is like kind of in the dimension through which it actually travels. So we would call this the length, right? The reason I bring this up is that kind of sometimes they'll talk about the width of the magnetic field versus the length of the magnetic field. So the length of the magnetic field would kind of be the way the magnetic field goes, right? So this would kind of be the length of the magnetic field if this is it. So when a wire goes through it perpendicularly, we are usually thinking about the width of the magnetic field. That's the part of it that is interesting to us. But again, this doesn't change any of the physics that we understand. It's kind of just a hoop that we jump through to say, okay, how much of the wire, what length of the wire is actually perpendicular to the magnetic field? Well, it's the portion that goes through the width of the magnetic field. Length and width are by definition kind of perpendicular to each other, right? Again, just a reminder of this guy that what is the current? Well, it's the charge in coulombs that flows through some point per second. So let's just get a little bit used to it. Okay, how many electrons flow through a wire each second if the current is 1 amp? So I is 1 amp. Remember, an amp is 1 coulomb per second. Time is 1 second. Now it says how many electrons? Well, if we can figure out the total charge, right? We know the charge of 1 electron, so then we can figure out the number of electrons that must have flown to give us that total charge. So I equals Q over T, right? Let's go ahead and call it Q total, just because it's the total charge produced by however many electrons. Okay, isolate for it, and then we have the total charge that is flowing through. It's going to be 1 amp times 1 second, and yes, it's kind of painfully obvious, right? It's if there's 1 amp, then obviously 1 coulomb is going through per second, but just kind of getting used to the formula. So Q total equals, remember an amp is a coulomb per second, so the seconds would cancel and we'd have 1 coulomb, okay? Now we'll come over here and say, all right, so if 1 coulomb is flowing through, the number of electrons is equal to Q total over the Q of an electron. Right, if I have $100 total and every student gave me $5, how many students do I have? Well, 100 divided by 5. That'd be nice if you all want to give me $5. Okay, so the number of electrons then is equal to, in total, whoops, 1 coulomb, sorry. Okay, so in total we have 1 coulomb of charge, okay, divided by, you can even think of this still, because these are the units, right? We have 1.6 times 10 to the negative 19 coulombs for every electron. So we could say per electron, right? These can be units. It can work out in a unit analysis way here. So coulombs over coulombs, and look at that. We're going to have 1 over electrons. So the number of electrons is equal to 6.25 times 10 to the 18 electrons. Coulombs per electron is a unit, just like dollars per student would be a unit. Okay, so now we're going to go back to what I was talking about with the width of the magnetic field and the length of the wire, just because this is an example that kind of illustrates what I was talking about there, how they kind of throw that at you. So they tell us the current, they tell us the magnetic field strength, they tell us the mass of the wire, which is this thing, right? The mass is 25 grams, okay? Now they tell us the total length of the wire, but here's where things get interesting. Is that whole thing inside the magnetic field, right? Is this whole thing inside the magnetic field? No, right? Only this little kind of sliver is. So when we're going to find the length that is perpendicular to the magnetic field, we need to just kind of chop that part off, right? Chop those two ends off because they're not going to feel the magnetic force. They're not in the perpendicular field. Okay, so then they tell us the length of the field, and we're saying, well, what does that mean? What's the length of the field versus the width of the field? So now returning to our idea, right? Looking at this guy, okay, I'm just drawing it from the front view. Looking at this guy, the field lines would leave north, enter south, leave north, enter south, right? See what I mean? When we say length, we kind of mean going along the field. Long, length, right? Along. So this dimension would be L of the magnetic field. We would think of that as the length of the magnetic field there, right? We don't want that though. We want, because our wire is traveling through like this, right? We just want this part that's perpendicular. So what we would call that dimension is what's perpendicular to length? Well, the width is, right? So that's width of magnetic field. So length of the field, great to know, but does it actually appear anywhere in our equation? Is it any help to us? No, right? We want the width of the field. That's what's going to help us out here. Okay, now the total length of the wire, great to know, but that doesn't help us, right? In fact, this is kind of sneaky. The width of the field, notice, what is that actually? The width of the field is actually the perpendicular length of the wire. See what I mean? This length right here, that is what is perpendicular to the magnetic field, and it just so happens to be the same size as the width of the field there, okay? So even, let's just clarify that. Width of field, that's the same as the length perpendicular of the wire. Make the wording a little bit less confusing. There we go. Okay, so determine the magnitude and direction of acceleration. Let's go ahead and just do direction first. I want you to look at this, okay? Now to tell me which direction is that wire going to accelerate. To figure out that, you have to figure out what direction the force it's going to feel is going to be, okay? So pause here, use your hand rules, see if you can figure out which direction the force will be that this thing feels. So since they've told us current, I'm going to go ahead and set up current to answer this, okay? You could use electron flow, try it the other way if you want, but I'm using current, and current would go from the positive terminal, try to get away from that and go towards the negative terminal, right? Of course, electron flow would just be the opposite. Okay, so hopefully you arrived at the same conclusion, but I've drawn in my right hand rule for this, right? So if you didn't get there, try it, right? Hold out your right hand, your thumb goes this way. The magnetic field lines, like we said, go up from north to south, okay? So your fingers should point up. And where does that leave your magnetic force pointing? Well, towards the back of the magnet, right? So FM would kind of be back towards the back of the magnet like that. So this wire is going to deflect in towards the back of the magnet. So there we go. We've already got our direction. Let's go ahead and get the magnitude. I honestly always find it easier to find the direction first, just so I can conceptualize what's actually going on here first, right? Whenever possible, I like to contextualize my number before I go ahead and get a number. So since we kind of did this already, let's just quickly do this. Actually explain how to determine the direction. Well, how do we determine the direction? We used current, maybe used electron flow. So don't say current if you use electron flow. So current, we are going to use the right hand rule. And we'll use the third one, right? Because we're dealing with an external magnetic field, a current, and a magnetic force. So what do we do? Sum in direction of the current. Fingers in direction of external magnetic field. And so then our palm shows direction of the resulting magnetic force. So if we were to draw a free body for the wire, say we're looking down the wire from this angle, okay, so our eye is kind of where our hand was in this picture. If we want, we could even say, okay, there's a current in. Okay, it's not a force, but it helps us just get a hold of what we're looking at. So what forces are acting on this? Well, we've worked out the magnetic force from that perspective would be off that way, right? What else is going on here? Well, it has mass, so it feels a force of gravity. Why doesn't it fall? Well, it's being held up by those little suspenders, right? So a tension force. Okay, now let's get an actual number. So where do we start? Well, the magnetic force is going to be equal to the current times the perpendicular length of the wire, which we said would actually be the width of the magnetic field, right? Now, it didn't ask for a force, it asked for an acceleration, but remember, right? Net force, yes, but in this case, since the tension and the gravity cancel each other out, the net force kind of is the magnetic force, and every net force is a mass times an acceleration. So, hey, we've got ma equals ILB. So the acceleration of this wire will be equal to current times the length of the wire that's perpendicular, which is really just the width that it passes through here, right? Only that part of the wire is perpendicular to the magnetic field. So that's 1.3 centimeters. And the magnetic field strength is 0.130 Tesla. All divided by its mass. Be careful, that's in grams, so divide by 1,000. And I got that the acceleration was, to 2 sig digs, 0.16 meters per second squared. What do we say for direction? Well, good enough is to just say towards back of magnet. Let's just do a quick unit check on this because we got the time. Hey, we're on a test. It's a free way to check our work. We might as well, okay? So let's just do a quick unit check. Unrelated to this question, but this is where I have room. So what do we have? We have amps times meters times Tesla divided by kilograms. And we're hoping that that's equal to meters per second squared, right? Because that's an acceleration. Okay, let's see. So we've got amps. We know amps are a coulomb per second times a length in meters times a Tesla. Do you remember what a Tesla is? Well, if you work it out, okay, it was a kilogram per coulomb second, all divided by kilograms. And now we go to cancel town. So coulombs over coulombs. See you later. Seconds times seconds. Okay, so those are going to get squared. But kilograms over kilograms. Oh, this is looking good. What do we got? We got meters over. We've got meters on top over seconds times seconds in the denominator. So look at that. Meters per second squared. Everything else is gone. Units are a wonderful thing. Okay, so before we jump into this next example, I just have a note on this. This apparatus, it would work, but it's kind of shown to you wrong. So imagine this whole thing kind of rotated 90 degrees that way so that it's sitting on this side here. Okay, so like if we put the table here and we turn our head sideways, this would work. Okay, the way they have it, it kind of wouldn't. You'll see why when we go to do it. You'll see why when we actually go to do it, okay? But you'll have to just imagine that this whole thing is turned sideways. Because as it is here, it wouldn't support the way it was supposed to. I think that is what they intended, but for some reason, this picture is this way. So I'm just going to really quickly redraw it from the angle that we kind of need to think about it as. Wow, can you believe I drew that by hand just now? Pretty good. Okay, so the idea here now, what changes is that before, which way would gravity pull it if this was actually how it was sitting? It would pull it down like that, right? As you can see, if you want to play around with your hand rules, there is no way for the magnetic force to support it against gravity if you go that way. So the apparatus is kind of meant to be used this way. So that gravity would kind of make this droop downward like a limp noodle, okay, like that, like a drawbridge, when the magnetic force is not there to support. All right, so a 23-gram wire is balanced in this magnetic field of 0.35 Tesla, 15 centimeters wide. The power supply is on so that the wire is balanced. What does that mean? Okay, because they keep throwing around that word balanced, and they really should say against gravity. So realistically, the picture of the apparatus isn't necessary, but it does kind of help clarify, unless in this case where we had to rotate it, because this doesn't really work. So the power supply is on so that the wire is balanced, and a student claims that the current causing this is 43 amps. This is actually the exact type of equipment that Ampere, who the amp is named after, okay, used to develop this equation, Fm equals ILB. So essentially, use the magnetic force to balance against the magnetic force. And once you've done that, since you know the thing's mass, you always know the force of gravity, essentially. So once you find the point at which those two are equal, you can figure out, okay, what other variables does it depend on? This is a lot like, you might be getting flashbacks to Millikan's experiment, right? What did he do? He balanced the electric force against the gravitational force. So gravity is a useful tool for us because as long as we know something's mass, we can kind of know the force of gravity it's going to feel, and then balance other forces against it to work out what variables are influencing that Fm and how much they influence and what the relationship is, right? So this one's kind of given us the answer and asked us, is it a good answer? So evaluate their result, include a free body diagram and a physics principle. So let's start with a free body diagram. So if we are this wire, why are we not drooping? Why are we balanced? Because gravity is pulling us down. So there must be something not allowing us to fall. Well, it's the magnetic force, right? So what does this lead us to? This leads us to the fact that, well, yeah, F net equals 0. Hey, does that sound like a physics principle? You bet. Newton's first law, right? Physics principle number 0, when the forces are balanced. There we go. Okay, so F net is 0. And what are the two forces here? Well, Fm plus Fg must equal 0. Okay, and so Fm equals negative Fg. Because it's a bit weird to deal with directions too seriously when we're talking about magnetic forces and we have all these perpendicular things, right? Because, for example, to now get Fm, I'm going to have to use magnetic field, and magnetic field is not in the same direction as Fm. To have this be meaningful, we kind of now need to say, right, if Fm is negative Fg, then the magnitude is equal to the magnitude of Fg, right? Just like you would do an absolute value in math class. Okay, the reason I say that is because, well, like I said, now we're going to say, if this is true, then ILB equals mg. Again, magnitudes. If ILB equals mg, let's see if this kid was right. Divide both sides by LB, and we'll be finding current shortly. I equals the mass times the gravitational field strength, or acceleration due to gravity, divided by the perpendicular length of the wire and the magnetic field strength. Go back to our question here, just look at our given K. So the magnetic field is 0.35 Tesla. That's the magnetic field strength. Okay, 15 centimeters wide. That's the width of the magnetic field. Okay, so looking at this, magnetic field's going this way, or whichever way. Maybe it's going the other way. We don't know which is north and which is south. But either way, it's going along that axis, right? So if we think about the width of that, the length goes along it, long length. The width would be that, right? That would be the width of the magnetic field, which, of course, that width that this wire is traveling through, hey, that's the length of the wire, right? That's the length of the wire that is perpendicular to the magnetic field. So really, this 15 centimeter wide width of the magnetic field, that's the same as the length of the wire that is perpendicular. So we have that the current is equal to the mass of the wire, which is 0.023 kilograms. Careful, don't fall for the grams trick. G is still 9.81 newtons per kilogram. Divided by the length that is perpendicular, well, 15 centimeters, so 0.15 meters. And the magnetic field strength, 0.35 Tesla. So when I did it, I got that the current was 4.2977 amps, or to 2 sig digs, 4.3 amps. Okay, so we found the current, but that question didn't ask us that. It asked us to evaluate the student's answer. So they got 43 amps. So they were off by a factor of 10. So student was off by a factor of 10. Larger. They had too big by a factor of 10. I look at this, okay, I've marked a few things in my day. When I look at this, I'm thinking probably the student made the common mistake of, when converting grams to kilograms, dividing by 100 instead of dividing by 1,000. That's the first thing that jumps out to me. That would be my first thing I would check if I was going to mark this question for a student. Okay, there we go. We've evaluated their answer. So they are wrong. So they are wrong, but probably for a Science 10 mistake, not a Physics 30 mistake, looks like. Okay, in the last question, if the current were tripled, what would be the resulting acceleration of the wire? Include a free body diagram and a physics principle. So let's just think about first, what if the current were tripled? Well, the force magnetic would be equal to still IL times B. So if we triple the current, right, we are going to triple the force. So I just say that so we can think about our magnetic field. Because if they were balanced before, well, now the magnetic force should be about 3 times as large as the gravitational force, right? Now sorry, did I say field? I meant magnetic force. The magnetic force should be about 3 times as large as the gravitational force. Okay, so to get the acceleration, well, the acceleration equals F net over m, which, what are the net forces acting on this thing? There is the force of gravity plus the magnetic force, all divided by the mass of the wire. Let's just go ahead and define some directions really quick here. We will make towards the top of the page up be positive, down towards the bottom of the page be negative. So then we have the acceleration is equal to Fg will be mg, g is going to be negative when we put it in, okay, plus ILB, and we're just going to leave that whole term positive because Fm is positive, right? It's towards the top of the page. All divided by the mass of the wire. So the acceleration is equal to mass of the wire, 0.023 kilograms. And because we're defining down as negative, that's the way G would go, the gravitational field. So negative 9.81 newtons per kilogram, plus ILB, the current we just found. Good thing we wrote down some extra sig digs, 4.2977 amps. The length perpendicular is the width of the magnetic field, so 15 centimeters. And the magnetic field strength is 0.35 Teslas. Again, we're going to leave that whole thing positive because we've defined up as the positive direction. Divided by the mass of the wire. So when you plug that all in, I got the acceleration would be equal to 19.62 meters per second squared, or 2 sig gigs, and with a direction, 20 meters per second squared. And we really can say up, right? Because looking at our apparatus, if it were done properly, that would be up. Okay, now bonus question for you. Use your hand rules. Let's say I drew this right, and this is the direction of the magnetic field. So this is north, this is south, and that really is the magnetic field direction. What has to be the positive terminal and the negative terminal? Where do negative charges need to be flowing to go, or where do positive charges need to be flowing from and to support this against the wire? Okay, I'll give you, okay, that's kind of my bonus deeper thinking. See if you can figure out which of these is positive, which of these is negative, if I'm correct about this being the magnetic field. What I ended up getting, if you want to check your work, is that would have to be the electron flow, which of course means current would have to be going that way, which would make this the negative terminal and that the positive terminal. By the way, sorry, what physics principle did we use here? We used physics principle, well, take a look. Which one applies the most? Which one did we really use here in making this calculation? This is just a Newton's second law question, right? This is just Newton's second law. F equals ma, or A equals F over m. So PP number 1. The forces are not balanced, and so there is an acceleration.